Welcome to week 3 of MAT 218, Mathematical Analysis for Business. The purpose of this video is to get you started on the first assignment in week 3. So if we click on week 3, which you should have access to now, and of course, as always, read the announcement. You'll notice that down at the bottom it says that I have posted instructor videos which explain my lecture outlines. Well, that's what this is the first one of. So make sure that you watch this. Hopefully it will be beneficial. Let me know if it is. I will continue to make more of these. So let's get started on the first assignment. So click on Introduction to Linear Programming and then open up the lecture outline. The lecture outline will look something like this. It's a PowerPoint. And the purpose of linear programming is optimization. We will have an objective function, some type of a function that we want to optimize. And optimize means either find a maximum value or a minimum value. And so we are looking for the optimum value of some type of a function, and it's always going to be linear. In the last unit that we finished up, we were dealing only with linear equations and systems of linear equations, and we learned how to solve systems of linear equations. So this right here is a linear equation, and it is the objective function. The thing that makes a linear programming problem unique is that the objective function is going to be subjected to constraints. And those constraints are going to be in the form of linear inequalities that look something like this. Cx plus dy is less than or equal to some value e. And remember from your study in algebra of inequalities, it is this less than or equal to sign or the greater than equal to sign that creates the linear inequality rather than a linear equation. So, in summary here, a linear programming problem consists of an objective function that we want to optimize, which means maximize or minimize, and it will be subjected to one or more constraints. So, let's take a look at some examples here. So, here is an example of a typical linear programming problem that you're going to be seeing for the next 2 weeks. It starts off by saying maximize p equals 0.12x plus 0.10y. That is the objective function. That is what we want to, in this case, maximize. We want to find the maximum value of p. Now, I always think of p stands for profit. We don't know that it necessarily stands for profit, but I like to think of it as profit because profit is something we want to maximize. So that's kind of helps to remember what P is. We want to maximize profit, and the equation for that is 0.12x plus 0.10y. Now, if we just let x and y be infinitely large, P would become infinitely large. And so we could just let x go to infinity, we could let y get infinitely large, and profit would get infinitely large. But that's where the constraints come in. They are subject to these 4 constraints. The value of x plus y has to be less than or equal to 25. Also, x has to be greater than or equal to 10, which means x could be anywhere from 10, and it could be decimals, 10, 10.1, 10.2. Negative x plus 2y has to be greater than 0. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. Now, these 2 constraints down here are what are sometimes referred to as the non-negativity constraints. It simply means that the values of x and y have to be positive. They cannot be negative. And that's typical of most linear programming problems. All right, and so this is another example of a typical linear programming problem. Now, the fundamental theorem of linear programming is that if a linear programming problem has optimal solutions, then at least one of these solutions occurs at a corner point of the feasible region. So there's a lot of terminology here. What is a feasible region? What do we mean by corner points? And so that's what we're going to explain. In this particular lesson, we are going to be using the graphical method. So it's just like when you started out with linear equations. You start off with graphing them so you can visualize what's going on. Tomorrow, we're going to get into the simplex method, which is a more algebraic technique for doing the same thing, optimizing the LP problem. So what we want to do is graph the feasible region and check that it is bounded, and I will explain what that means. Compute the coordinates of the corner points of that bounded feasible region. Substitute the coordinates of the corner points into the objective function to see which gives the maximum or minimum value, depending on what we're looking for. And any such corner point is an optimal solution. So you can come back to this slide. Let's take a look at the first example. Now, I'm going to encourage you to use Desmos. If you feel more comfortable using a graphing calculator, you may use that, but I'm going to be using Desmos. So this first example is we want to maximize P equals 2x plus 3y. That is the objective function. The constraints are 2x plus 5y must be greater than or equal to 5. 5x plus 2y must be less than or equal to 10. And the opposite of x plus y has to be less than or equal to 2. So I'm going to start by going to Desmos. And there's a link to Desmos in the course resources. And let's just enter in the constraints. So to enter in the constraints, it's simply type in 2x plus 3y. You don't need to type in asterisks or anything or multiplication. Oops, I'm sorry, 2x plus 5y. That's the 2x plus 5y. Now, to get the greater than or equal to 5, simply type in the greater than symbol and then the equal symbol and then 5. Now, this is what's nice about Desmos. It graphs that line for you and it shades on the appropriate side of the graph. So you may want to back up a little bit and review graphing linear inequalities. Just as a real quick review, whenever you have a linear inequality, you always shade on one side of the graph or the other. And that's because the solutions are sometimes on the graph. In this case, there will be solutions on the graph. And also, anything up in this shaded region will be a solution to this linear equation, such as this point right here, which is the point 1, 1. Where I'm pointing at. That point right there is 1, 1. If we substitute 1 in for x and 1 in for y, we get 2 times 1 is 2, plus 5 times 1 is 5. 5 plus 2 is 7. 7 is greater than or equal to 5, so that's true. And since 1, 1 is on this side of the line, and it is a solution, every point on this side is a solution. So anyway, this wasn't meant to be a video on graphing linear equalities. If you need to, you can go to YouTube and find lots of videos on that. Let's go to the second inequality, or constraint. The second constraint was 5x plus 2y. So 5x plus 2y is now less than equal to 10. And it's shaded. I don't like that color, so here's what I'm going to do. I'm going to click. Okay, let's go to edit. Oh, we'll just keep it that color. Third inequality is negative x plus y is less than or equal to 2. So it's graphed all three of these linear inequalities, and it's shaded on the appropriate side. Now, what we are looking for, let's zoom out a little bit. What we are looking for is the area that is common to all three inequalities. So in other words, the first inequality, all the area of the graph above the line was shaded blue. Then this inequality right here, everything over here was shaded. And then the third inequality, we have everything over here was shaded. So the area that they all have in common, the overlapping shaded area, is this triangle right in here. Okay, this triangle is shaded from all three of the linear inequalities. That little triangle is our feasible region. Right? That's the region where we're going to find the solution. And it's completely bounded. In other words, it's completely enclosed. So let's zoom out a little bit. What we want to do now is find the corner points, because remember that fundamental theorem of linear programming said if there's a solution, it will be at a corner point. So the nice thing about Desmos is click on the line, click somewhere in the line, and it'll tell you what the corner point is. 0.857, 2.857. Click on this line. It gives you that point again, but also this point. Negative 0.714, 1.286. And click on this one, and we can get this point down here, 1.905 and 0.238. So those three corner points of this feasible region is what we want to, let's go back to the slide. So that's somewhat of what it looks like. We want to make a little table. You have an X column and a Y column. It's kind of like a matrix. And you can do this by hand. And here are the corner points, the X and the Y value of the corner points. Now here I rounded them to the tenths. In Desmos it was rounded to the thousandths, I think. And one more step and we are done. So in the last column, I have the objective function, p equals 2x plus 3y. So all we have to do now is put in the 1.9 and the 0.2 for y. So 2 times x, or 2 times 1.9, plus 3 times y, or 3 times 0.2, is going to be equal to 4.4. Then the second point, 2 times negative 0.7, plus 3 times 1.3 is 2.5. And finally, 2 times 0.9 plus 3 times 2.9 is 10.5. Right, so these three values here are our p values. P is 4.4, P is 2.5, P is 10.5. We're looking to maximize P. So what we have to do is pick the largest of those three numbers, 10.5, and that is the answer to our problem. So what we just did were these four steps. We graphed the feasible region and checked that it was bounded. We computed the coordinates of the corner points. We substituted the coordinates of the corner points into the objective function, and any such corner is an optimal solution. And so we found out that the optimal solution, if we're maximizing, is the largest of these. And that is the first example. And I believe I'm going to leave this video because this has been about 13 minutes. I'm going to create another video with two more examples, one more bounded and one more unbounded, and I will be posting them right underneath this video. So I hope this was helpful, and let me know if you have any thoughts or questions.